now our last speaker, that is Mattia Antonini, who is a researcher in the Open IoT research unit at Bruno Kessler Foundation, Trento, Italy. He received a PhD degree in computer science from the University of Trento, and he has been a member of or a visitor of international and multidisciplinary research groups. He has actively contributed to local, international, and European research and innovation projects. So, give him a warm welcome.
Thank you, Valeria. So, good morning to everybody. Can you hear me in the back? Okay, cool. So, today I'm going to present our current activities at FBK, so about Tiny-MLOps. And that's a strategy to orchestrate machine learning applications at the edge of the network, but even beyond. But before starting, I'd like to present a bit how I landed in those beautiful mountains that are the Dolomites. Because I joined the foundation when I was an intern during my master, and then decided to move there because those mountains are literally beautiful. And then now I'm a researcher there after my PhD. If you want to contact me, here are the contacts, so feel free to drop me a message. So now let's dip to some nice and fancy stuff, if it works, of course. So let me give you some background. So we know that intelligence is moving towards the edge. But the fact is that the applications are embracing also the infrastructure. So it's not just to push at the model on a device, but we need also to move the model over the device. And you know that pipelines and the models can be executed really close to data sources. And this enables new kind of applications where that are latency sensitive, but even context aware and data sensitive. So the data are processed there, we know. However, there are a few problems, of course. First, there are literally a gazillion of different computing platforms. So we need to handle this problem. Of course, most of them offer just a few computing resources. That's another problem. So we need to optimize the model to deal with that. Of course, sometimes the models cannot be connected to the internet. So we cannot rely on external cloud to handle the intelligence. And of course, usually these devices are battery powered. So we need also to optimize the energy in order to enlarge the lifespan of devices. So, as I said, we have literally different gazillion of devices. Usually we have two main classes of devices in the edge. The single board computers that cost between 20 to 100 euros, more or less. Like I'm talking about Coral board, Raspberry Pis, Jetson Nano, and usually these run full-fledged operating systems. So also they support cloud-native technologies, for instance, Docker, Kubernetes, or similars. Of course, they are really energy demanding. And also, if we want to deal with the machine learning operation over these devices, we can use cloud-native platforms. There are the other class, which are the microcontrollers, of course. In this case, the cost is around a few euros. They usually run a real-time operating system. And is vibrating? I don't know why. Probably is. OK. They support over-the-air update. Of course, they consume just a bit of energy. However, there isn't any uniform approach to bring a model to the target platform. So we need to deal also with different tool chains, different architectures. So what we want to do? We want to solve a proportion. So we know that MLOps can be applied to single board computers. But what can we do with microcontrollers? We need to find the X. I know, spoiler alert, the X is there. But what's the X? It's what we call Tiny-MLOps. So what we did, if it works, OK, now it works. So the latency is pretty high. OK. OK, cool, thanks. So if we want to build an application with Tiny-MLOps, we need to follow the Tiny-MLOps loop. That is similar to the original MLOps loop, and also was presented this morning. But we extended it to keep in mind that we want also to deal with microcontrollers. So the first step is, of course, the planning. So we need to explore the data, if we have it, of course, and we just need to start the features that we're going to use. Then we have to train and create the model. And also we need to optimize the features that we're going to use. Following, once the model is trained and created, we need to adapt and optimize the model for a target platform. For instance, we apply post-training quantization. We also use some tools to optimize the device, to optimize, the model. OK, wrong button. And then we have to check if the model literally is executable over the target platform. I'm talking about, for instance, we have to check if for instance, I don't know, if you have an neural network, sometimes you know that some operations are not supported. And this is a problem, because we have to check back to the main controller, and sometimes this turns in huge memory usage or a lot of energy wasted, and so on. So we need to check this. And all this, the blue part, is mainly handled by data scientists or data engineers. So now we have our model ready for, let's say, to be bring to the outside world where it should be executed. We need to package it, because the model is not ready to be literally put over the device. So we need to compile and convert to the target platform and make it ready. Then we need to load the model inside the memory of the device. We need to configure sometimes some parameters of the device. For instance, if I have an unsupervised learning algorithm, I need to configure, for instance, a detection threshold. And then we put it in production, and we have to monitor the model. Because, we need to check if it is behaving as expected. It may happen that some condition appears, something happens, so maybe the model does not work well. We need to trigger another iteration. And usually, these steps are handled by the ops engineers, operational engineers. OK, I just gave you a quick overview on how Tiny-MLOps works. But you can say to me, does it work? Let's see. So I'm going to propose you a real use case, a real industrial use case. And this use case is literally extreme. Why I'm saying extreme? It's extreme because there are extreme environmental conditions and extreme computational conditions. First, so the context is a wastewater management plant. These plants are essential for our lives because they handle the water from the sewage before returning the water to water streams like lake, rivers, or the sea. You know that these plants are made of pools where there are water that is moved from one pool to the other with pipes, with pumps, and so on. And during every step, the water is purified. The fact is that inside the pools, there are these pumps that are literally below meters of water, and this water sometimes is really corrosive, and it is quite hard to deploy this device in this scenario. That's why I'm saying it's extreme. High pressure. Of course, the device has to be leak-proof, and so on. So we need to handle with these extreme conditions. And also, the fact is that usually we cannot deploy new cables to bring outside to bring inside energy for the device or for communication. So we need to exploit what we have. And this is really a challenge. So the challenges of this use case are threefold. So first, we want to deploy a condition monitoring system in these extreme environments where we have extreme, literally, constraints. Of course, as I will present later, we cannot rely on traditional supervised learning. We are going to use unsupervised learning. And we are not using neural networks, but we will use another kind of algorithm. So we need to target the target operating conditions. And of course, we want to improve the schedule maintenance of these pumps, because usually the schedule maintenance is based on a time schedule. So every, 1,000 hours, the bearings are replaced. And this turns in high operational cost. We want to improve this stuff, because sometimes, for instance, bearings can last for other 4,000 hours. So why I have to change a bearing when it is only it works only for the 20% of its lifespan? So what we did is to build a scenario where we have the pump, of course, connected to the high-power AC line. Usually, this pump are really huge. We're talking about from 10 to 100 1,000 kilowatts. So it's not just a small pump. And what we did, we placed inside the terminal chamber where there are the cables to power up the pump, a simple sensor kit. This kit has to be fully autonomous. So we have some vibrational sensors that collect vibration over the different axes and the temperature sensors that is necessary to sample the physical variables of the pumps. Then we have a computing unit that we run our algorithm. And then also we need some additional electronics. First, we need a power unit that has to be connected to the high power AC line. And this one has to guarantee a galvanic isolation from the line. In this way, we are sure that if there is a spike, for instance, when the pump is turned on, there are huge spikes of current. And this may destroy the device. So we don't want that, and because it may burn, literally. So we don't want to destroy a pump that costs thousands of euros. And the same, we need to deploy a communication unit that is able to convey waves over the AC power line. We exploit power line communications. In this case, the bandwidth is below 2 kilobaud. So we need also to optimize the communication aspect in order to be sure that we can send some stuff outside. Indeed, we will send just some notification like, I'm alive, everything is OK, every here and then. And also when an anomaly happens, we say, OK, so the system will be anomalous. Please check if something is happening. We'll see later. And then we have something outside that collects the notification. And maybe we have something in the cloud, but just, for instance, for dashboarding and other stuff. OK, so how it works. At the beginning, when we deploy the system is not trained. So we want to train the model directly inside the pump. So we are going to use an unsupervised learning approach based on isolation forest that is similar to random forest. So at the beginning, we have we have the data that start flowing from the sensors, and it goes inside a feature extraction module where we compute some meaningful features. Then data flows to the local training engine, where it starts training the model over the data that it receives. We assume that now the engine is working in a normal condition. Then, once the model is ready, we configure some detection threshold, and then we place in the local inference engine. Now the model is deployed and is ready to work. So here we switch over the feature select extraction module, and now data start flowing over towards the local inference engine. Now, if everything is OK, we are lucky. But sometimes we are not. So maybe there is some wood that enters in the fan, so there are some strange vibrations. Or maybe it was a really rainy day, so the density of the water decreases. And now the fan is vibrating in a different way, so it can be anomalous. So we send notifications towards the outside world over the PLC channel, and it is handled by an anomaly manager. Here, this can be implemented based on the business logic of the plant or the application. Then we present some fancy stuff over dashboard, like saying, oh, we had just one anomaly over 48 hours. So, OK, that was a false positive because there was a branch inside the fan. It happens. So that's why I'm saying that. And here, maybe, we have the scientist or engineer that may take decision over the system, because we know that this kind of systems are always supervised by people. We don't want to remove the people. We need experts, literally, because these plants are essential. But we want to improve their work, and we want to simplify their job. So if something I have to take over the system, they can send commands or send a new model or new features towards the local training engine that will start the training, and it will train a new model. And then place back in work, and the loop restarts, and so on and so forth. So the issue is that this kind of systems are really expensive, and acting over this kind of system is tricky. So when we want to deploy the system, we need to be sure that everything works, because we cannot open the gasket, open the chamber, replace the device, because I forgot that file. So I forgot I need to change the firmware. So when it's deployed, literally is deployed. Every time that we extract a pump, it costs 1,000 euros. So we need to optimize also these aspects. So we built a vibrational simulator. That is funny, I know. It's just a simple PC fan suspended over some springs, and we can perturbate the system by touching it, so we can inject literally artificial anomalies. As I said, the model is based over isolation forest. If you want more details, there are the papers, or we can talk later, and so on. And then we perform some tests before deploying the system. And this system is now currently deployed in a real plant in northern Italy. And it's working pretty well because the company didn't say that it's not working, so I think that it's working, I hope so. OK, so let's bring TinyMLOps at home. So we know that we want to deliver continuously features and also AI applications. And usually, when we deal with Linux-powered devices, we can use traditional MLOps tools. In this case, we are in a constrained world. So we need to keep in mind that there are strong challenges, strong constraints, and how can we deal with them? Of course, the TinyMLOps loop is based on MLOps loop, so it handles everything that is being handled by the MLOps loop. But it adds some additional steps that are useful for the tiny world. And also, we applied in a real-world scenario. OK. New scenarios, new questions, new challenges. It's possible to optimize the deployment of models. And also, how can we select the best model in these cases? And also, the federated approaches can be a solution in this, like big scenarios where we can have like tens or hundreds, for instance, of different engines. How can we exploit, for instance, this kind of approaches in this kind of scenarios? So thank you. If you have any questions, I'm here to respond to you. If you're interested, also we are hiring. So.